everyone, this is Babitha, working as Assistant Professor in the Department of ECE, Institute of Aeronautical Engineering. In this session, I am going to discuss about the different capacitors which are existing in the metal oxide semiconductor field effect transistors, that is MOSFET. So while coming to the contents, just we will discuss about MOSFET and its related capacitances in the operation of the MOSFET. So before going to the MOSFET capacitors, first of all, we have to know what is meant by capacitor and what is the values of different capacitors and which type of capacitors which are going to exist in the case of MOSFET circuits. We are going to see now. Generally, capacitor, it is a device which can be used to store the electrical energy here. That electrical energy in the form of electrical field, it will store here. And this capacitor, we can call it as the passive element or a passive component, and it consists of two terminals. And the effect of the capacitor, we are calling it as the capacitance here. So if we connect any capacitor with the battery, it can able to store the charge in the form of electric field here. And here we can observe in the picture different types of capacitors. Here these kind of capacitors are the ceramic capacitors, and these are the electrolytic capacitors, and these are another kind of the capacitors here. So depending upon the which type of materials we are utilizing to construct the capacitors, these are divided into different types here. So depending upon our practical applications, we can able to utilize any one of the capacitor here. So the capacitance value will measured in farads here. Okay, the unit for the capacitance is farads here. And so I have already mentioned capacitor is a device which can be used to store the electrical energy, and it consists of two conducting plates here. Okay, it consists of two conducting plates, or we can call it as two conductors here. So the two conductors I'm showing here, these are the two conductors, acts like a two plates of the parallel plate capacitor here, and in between these two plates there is a insulating medium will be present, that is the dielectric medium. So this dielectric medium acts like an insulator between these two conductors. So conductors having high conductivity, those can able to allow the large number of charge carriers, that may be the electrons or holes, depending upon which type of conductor we are going to utilize. And insulator is a material which doesn't allow the flow of electrons through it. So the conductivity of the insulating material is almost zero. Okay. So between these two conducting plates, we are having dielectric medium acts like an insulator here. Okay. So here this particular plate is storing the positive charge plus Q, and this particular plate can able to store the negative charge Q minus here. So one plate is storing the positive charge, and one more plate is storing the negative charge. So the equal amount of negative charge is deposited on the second conductor. So first conductor is having positive charge, the same amount of negative charge can be stored by the second conductor. So now we can say the capacitor is having with the charge Q here. So in this way the capacitor can able to store the charge within the two parallel plates. And while coming to the capacitor circuit, when we connect a capacitor to a battery, what will happen here, it is the plate on the capacitor that attached to the negative terminal of the battery accepts the electrons that the battery is producing here. Okay, the negative here, we have already mentioned that it is having two plates. One is the negative plate and one is the positive plate for the capacitor circuit. So if we connect the negative terminal of the battery to the capacitor, so that what will happen here, the electrons which are generated from this battery are attracted towards this positive plate. Okay, and next the plate on the capacitor that attaches to the positive terminal of the battery loses electrons to the battery here. Why? Because it is accepting these particular electrons, and these particular electrons are attracted towards this battery, this positive terminal of the battery here. So in this way, it is formed like a circuit, so that it is formed like a closed circuit, and it can able to store the charge in the form of flow of electrons here. So that is due to the application of the battery voltage to the capacitor here. So while coming to the different types of capacitors, actually capacitors are having two types. One is fixed type capacitors, and one more is variable type capacitors. So how we can able to differentiate whether the particular capacitor is the fixed capacitor or a variable capacitor means, in this case the capacitance value is fixed. In the case of fixed capacitors, the capacitance value is fixed. But in the case of variable capacitors, the value of capacitance is varied between some range here. So in most of the cases, for any practical applications, we will utilize the fixed capacitors, not the variable capacitors. We will not preferable these particular variable capacitors compared to the fixed capacitors here. So that's why I'm going to discuss about the fixed capacitors only. So these any type of fixed capacitors we are going to utilize in the electronic circuit designs or electronic equipment. So these fixed capacitors are of two types. Those are non-polarized capacitors as well as polarized capacitors. And in the case of non-polarized capacitors, again we are having three types. That is MOS capacitors, and ceramic capacitors, and film capacitors. So in these MOS capacitors are designed with the vacuum tubes or air or glass or silicon type of materials, and the ceramic capacitors will design with the class 1 class 2 type of materials. So the examples for this class 1 and class 2 are given here. And while coming to the film capacitors, are designed with metallized and film or foil type of capacitors. So these metallized capacitors are designed with the paper, and these film capacitors are designed with the different sizes and different types of films here. And while coming to the polarized capacitors, we are having two types again: electrolytic capacitors and supercapacitors. In most of the applications, mostly well preferable this electrolytic capacitors in the practical applications. So these electrolytic capacitors are again divided into three types. Those are aluminum electrolytic capacitors, tantalum electrolytic capacitors, and non-niobium electrolytic capacitors here. So while coming to the aluminum electrolytic capacitors, these are formed with non-solid materials or hybrid polymers or solid polymer type of materials. These can be designed. And while coming to the tantalum electrolytic capacitors, these are also non-solid and solid type as well as solid polymer type of materials we can utilize. And in the case of niobium, we can utilize solid as well as solid polymer type of materials we can utilize to design such type of capacitances. And while coming to the super capacitors, we can having double layer capacitors as well as pseudo capacitors. So these are called as hybrid capacitors, having four classes of types. So these super capacitors are used to store huge amount of charge here. Why? Because the size of this one is very bulky and plates of this capacitor is also very high, so that those can able to store large amount of energy into it. So among all these type of capacitors, so depending upon our requirement, we can utilize any one of the capacitors for the designing of the practical applications. And where we can use these capacitors. So mostly these capacitors we can utilize in the digital circuits. So where we can use in these digital circuits means the information which can be stored in large computer memories is not lost during a momentary electric power failure. That is nothing but if the power failure is there, in that case also digital circuits can able to store the energy that is due to the capacitors which are present in the electrical circuits. So the capacitors which are present in the digital circuits can able to store that information during the temporary loss of power here. So the capacitors are the basic requirement for the digital circuits to store the information. And also these capacitors can used as filters to divert spurious electrical signals and that will prevent damage to sensitive components and the circuits caused by electric surges. That is nothing but any variations or any noise level of signals or any electric surges are appearing across the electronic circuits that can be filtered out by the capacitor. Why? Because capacitor can be able to allow only AC signals and it opposes the DC signals here. So because of that reason, it can able to allow the original signals and it will nullify the distorted or noisy signals. So that's why we can call it as the filter circuit. Or for designing the filtering circuits, we can able to utilize this capacitance. And just now we have seen now what is meant by capacitor and what are the different types of capacitors and what are the applications of capacitors. And now we'll go with the MOSFET capacitances. So before going to the MOSFET capacitances, first of all we have to know what is meant by MOSFET. So MOSFET is nothing but metal oxide semiconductor field effect transistor. It is the metal oxide semiconductor field effect transistor. So to design this MOSFET, suppose I wanted to design any N type of MOSFET, I have to take one P type of substrate here. This is P type of substrate and we can also call it as body. So we can represent it as the body terminal. So in the MOSFET we are having the source, drain as well as gate terminals, as like in the case of bipolar junction transistors. Here also we are having source, drain and gate terminals. So on this substrate, in order to create the source and the drain terminals, I am inserting some small pieces of N type of materials. Some small pieces of N type of material I am inserting onto the P type of substrate. That is nothing but P type of semiconductor material. And after this, I am placing some silicon dioxide layer here. This is silicon dioxide layer here. So upon this, okay, the gate terminal is present. So this is the drain. This is the source. Okay, source, gate, drain terminals of the MOSFET here. So this silicon dioxide layer which is present on this MOSFET, so that's why it is called as oxide. And metal layer we are utilizing in order to make the contacts between the terminals as well as that particular regions. So this metal is utilized to give the terminal for the drain region, and this metal is utilized to give the terminal for the source region, and this metal layer is utilized to give the terminal for the gate region here. So in this way we can form the MOSFET here. So the function of this MOSFET always depending upon the two voltages, that is the voltage which is applied between the gate and source terminals and voltage which is applied between the drain and source terminals. So depending upon that, the MOSFET or any kind of FET can able to operate here. So that's why any kind of FET we can call it as the voltage control device. Why? Because the current conduction in the FET is due to either VGS or VDS voltage here. So even though VGS voltage is 0, some amount of drain current can be flowing in the MOSFET due to the application of drain to source voltage here. Okay, and in this case it will operate in 3 regions, that is the ohmic region or saturation region or cutoff region, depending upon the how much amount of voltages which are present, how much amount of voltages we are applying across the gate to source terminal as well as across the drain to source terminal here. And when the VDS voltage is maximum, means at that case we will get the maximum drain current here. And whenever the VGS voltage is 0, the current is constant. So that current we can call it as the saturation current or saturation drain current here. So this is a simple explanation related to the MOSFET. So when we are performing the operation on the MOSFET, some different capacitors which are existing in the MOSFET. What are those different capacitors? We will see now. So if we take any particular device, we'll having some 2 to 3 types of capacitors which will be existing in the any type of electronic circuit here. So in that one type of capacitances we can expect in any device is stray capacitance. So what is mean by this stray capacitance? In order to understand this, I'm considering one silicon chip. I'm considering one silicon chip, and I wanted to insert some 2 or more conductors on this particular chip. Okay, so in between these conductors, there is a gap is present. There is a air or gap is present. So this air or gap will generate the capacitance between these 2 conductors. So these capacitances are known as the stray capacitances. We are not inserting intentionally in the circuit, but because of the construction point of view, or because of when we are inserting the conductors onto the chip, because of that reason, these capacitances are existing. We don't know whether they are existing or not. We cannot see these particular capacitances because we are not inserting physically these capacitances between these conductors. Okay, so these are unintentional capacitances which are existing in the different types of devices. Those are called as stray capacitances. But along with this, we are also having different type of capacitors in the MOSFET circuit. So for that purpose, I am taking the MOSFET here with gate, drain, and source terminals. So across the gate terminal, we'll be having one capacitor. So that capacitance, we can call it as the gate capacitance. And across the drain terminal also, we may have one capacitance. So that capacitance, we can call it as the drain capacitance. And across the source terminal also, we will be having one more capacitance, that is the source capacitance. So these 3 are the physical capacitors which are present in the terminals of the capacitors. Okay, 3 physical capacitors, those are gate capacitance, drain capacitance, as well as the source capacitance. So along with these 3 physical capacitances and 3 more capacitances which are existing in the 3 terminals of the MOSFET. So what are those means? Here, one capacitor will exist between the gate and source terminals of the MOSFET. So that capacitance we can call it as the gate to source capacitance. And one more capacitance is existing between the gate and drain terminals, that is the CGD capacitance. And one more capacitor existing between the drain and source terminals of the capacitors. So total 6 capacitors. These 3 are the physical capacitors, and remaining these 3 are the internal capacitances which are existing between the terminals of the MOSFET here. And these are occurring due to the conducting plates generated in the MOSFET circuits. So these MOSFET internal capacitances, how they are existing, we will see now. So for that purpose, whenever the gate voltage is applied to the MOSFET, the device will enter into the on condition. So there is a channel exist between the source and drain here. There is nothing but if we take the MOSFET circuit. Okay, so here this is the substrate of the MOSFET, and here these are the source and drain terminals. And this is the gate terminal here. So for this particular MOSFET, when we apply the gate voltage, that is nothing but between the gate and source, if we apply the voltage, VGS voltage, then because of that application of the gate to source voltage here, the electrons which are present here are will ripple from this source terminal and they are moving towards the this particular terminal. Sorry, here I am applying negative and positive. Okay, so the electrons which are present in this P type of substrate are attracting towards the positive terminal of the battery. That positive terminal is connected to the gate. So these electrons from this P type of substrate are attracting towards the gate terminal. So because of the application of gate to source voltage, the electrons which are present in the P type substrate are coming near the source and drain terminal. So these formation of the electrons will create the channel between the source and drain terminals. Okay, between the source and drain terminals, it will create the channel here. Okay, there is a channel exists when we apply the voltage to this between the source and drain terminals here. And whenever that particular voltage we are applying VGS voltage between the gate and source of the MOSFET, there are two types of capacitances will occur in the MOSFET. What are the two capacitances effects are means? That is gate capacitive effect and next junction capacitive effect. So this junction capacitive effect existing between the source and body as well as the drain and body terminals of the MOSFET. Already we are having the drain, source, gate and body terminals in any MOSFET, but in most of the cases we will combine this source and body terminal as the source terminal only. So now we'll discuss about gate capacitance which is existing in the case of MOSFET circuit. So in the case of gate capacitance, it is formed between the gate electrode and the channel. And in that case, the silicon dioxide layer which is present between the gate and channel acts like a dielectric between the gate and channel here. So that is nothing but here. I'm considering the MOSFET circuit to understand this gate capacitance with the terminals drain as well as source terminals, and upon this we are having silicon dioxide layer, and upon this we are having the gate terminal G here. Okay, so this gate terminal acts like one of the plate of the capacitor or one of the electrode of the capacitor, and the channel existing between the source and drain terminals acts like a one more electrode or one more plate of the capacitor. And whatever the silicon dioxide layer which we are utilizing in the construction of the MOSFET, this acts like a dielectric medium between the gate and channels of the MOSFET. So because of the presence of this gate silicon dioxide layer and channel one capacitor existing in the MOSFET, that capacitance we are calling it as the gate capacitance. So how much amount of capacitance which is present we can estimate by using the area how much it is occupied here. So that we are indicating with the COX here. So where COX is nothing but the capacitance per unit area here. And always this one also depending upon the plate, the size of the plate as well as how much amount of insulating material which is present between that plates. And second type of capacitance we can expect in the case of MOSFET is junction capacitive effect, that is between the source and body and draining body. So this junction capacitance effect we can expect whenever two type of semiconductor materials are joined together. That is nothing but for that purpose I am considering one P type of material as well as one N type of material. And if I join together these two type of materials, the depletion region will be formed between these two plates. So this particular region we can call it as the depletion region. So this depletion region acts like a dielectric material here or dielectric medium here. Okay, so this P region as well as N region acts like two plates of the capacitor here, and this depletion region acts like a dielectric medium between these two plates. So this particular capacitance which is existing across this junction of P and N type of material is called as junction capacitance. So between any two type of materials across the junction of the two type of materials, if the capacitance is existing, means that particular capacitance we can call it as the junction capacitance. So similarly, in the case of a MOSFET also, we can able to get two different types of junction capacitances. So those are, one is across source and substrate, this is one capacitance, and one is across drain and substrate. So this acts like a dielectric medium here. So these two are the junction capacitances we can expect in the case of MOSFET. Okay, so one capacitance between the drain and substrate. So this is the capacitance between the drain and substrate. I can write it as CDS, and this is the capacitance which can exist between the source and substrate. This is the substrate terminal, or we can also call it as body terminal of the MOSFET. So from the MOSFET operation, we can able to get the internal capacitances as well as junction capacitances. And we have already discussed the gate capacitive effect as well as junction capacitive effect in the case of MOSFET. So from the gate capacitive effect, we can able to get three types of capacitors in the MOSFET, and from the junction capacitance effect, we can able to get two types of capacitors here. So here, in order to find the values of these capacitances, how much which are existing in the MOSFET circuit, here we require different terminologies here. In order to represent any DC term, we will always represent the capital letters. So here VAB is nothing but the voltage between AB terminals or AB points. V capital AB is, we are to represent the DC terms, we are utilizing the capital letters. And to represent the AC terms, we are utilizing the small letters here. And if you want to represent the mixed signal here, that is AC signal is superimposed on the DC signal, in that case we can represent here it as small letter with subscript capital letters. And if capital letter with subscript small letter means if we want to represent any frequency related terms, we are going to utilize these particular notations. So these notations are very important in the MOSFET circuits or any electronic circuits in order to see the performance of that particular circuit. So while coming to the gate capacitances calculation, these gate capacitances we are going to calculate in the 4 regions of the MOSFET. Why we are going to calculate in the 4 regions means the MOSFET will operate in 3 regions and one more region will occur due to the extension of the materials while constructing the MOSFET. So what are the three regions we'll see now? One is the triode region, and one is the saturation region, and the cutoff region, and the extension of the materials in the circuit. So because of these four regions of operation of the MOSFET, these particular capacitor values we are going to calculate in these four regions. So in that I'm moving for the triode region first. So in the triode region, just the channel is formed between the source and drain terminals very uniformly. Why? Because we are providing a very less amount of gate to source voltage as well as the drain to source voltage to the MOSFET. So because of that reason, the uniform channel formed between the source and drain due to the uniform charge carriers uh, are accumulated near the channel. So for that purpose, I am indicating the MOSFET with the source and drain terminals. And here we are having the metal oxide region, and this is the gate terminal. This is substrate terminal here. So in this case, the channel, whenever the voltage is applied, the channel is formed between the source and drain terminals of the MOSFET. So this channel, the capacitance which is existing in this particular triode region, we can estimate by using the width and length of the channel, how much amount of charge carriers are accumulated near the junction, how much width and how much length the charge carriers are occupied here. So depends upon that we can able to estimate the how much amount of capacitance is existing in the channel. So for that purpose, I am taking only the channel here. So this is the channel. This is the gate material. So it is extended in this way. So this is the length of the channel and this is the width of the channel. Only this particular region I am representing here. Okay, this much extent the channel is existing here. So in this case, the capacitance I am representing here with the WLCOX, where W is the width of the channel and L is the length of the channel. So WL indicates the area of the total channel here. So in this triode region, channel is uniformly formed between the source and drain terminals, I have already mentioned. So that's why the capacitance is equally divided across the source terminal and across the drain terminal. So that's why I can write the capacitance which is existing between the gate and source as well as between the gate and drain. We can write it as 1 by 2 WLCOX. COX is nothing but the area of the capacitance, how much it is occupied here. So WL into COX, 1 by 2 into WL into COX. Why? Because same capacitance is distributed here as well as here. And the next region is saturation region. So when the MOSFET is in saturation region, the channel is pinched off at drain and towards the source here. Why? Because here in this particular case, this is the source, so drain source and gate terminal here. This is N plus. So in this particular saturation region, whenever the VDS voltage is increases, okay, drain to source voltage is increases means in that case the electron VDS voltage means we will apply in this way between the drain Okay, this positive terminal and negative terminal of the battery. Negative terminal of the battery is connected to drain and the positive terminal of the battery is connected to source. So what will happen here? It is channel already existed here. Okay, uniformly it is existed in the ohmic region. But when we increase this VDS voltage, the electrons which are present in this particular N region are attracting towards this source terminal. Okay, if we increase still more means more number of electrons will attract towards the positive terminal. So the number of electrons in the channel which is present here will be reduces now. So the number of charge carriers or electrons are reducing means the length of the channel is also reduced as well as the width of the channel is also reduced here. So now the channel will move to here. Now it is here, but when it is here when it is in the triode region, but in the saturation region, whenever we are increasing the VDS voltage, the channel is pinched off from drain to towards source terminal here. Okay, so the channel is pinched off here. So because of pinching off this channel, so the number of charge carriers will be reduced here. So because of the reduction of the number of charge carriers, the capacitance value will also reduced in the case of saturation region here. So that's why in this case we are writing the total capacitance is 2/3 of area and capacitance here. Okay, there is nothing but only 2/3 of capacitance will only exist in the saturation region. That is only gate to source voltage, gate to source capacitance only this much 2/3 WL/COX, but drain to source voltage is 0 here. There is no capacitance is present between the drain and source here. Why? Because there is no physical connection between the drain and source here. And next one is the cutoff region. So in the cutoff region, there is no channel formed between the source and drain terminals. So once the channel is not forming means there is no capacitance exist between the gate and body here. So that's why all the capacitors are 0 here. Gate to body as well as drain to body capacitances are 0 here. But gate to body as well as drain to body capacitance are 0, but gate to body capacitance is total capacitance which is present, that is width and length as well as COX of the MOSFET. So in this case I can represent like this. We are having all the terminals, that is drain, gate and source terminals, but there is no existence of the channel here. Because of that reason only we are not getting drain to substrate and source to substrate capacitances. But between gate and substrate always the capacitance is present. Why? Because these two materials acts like two parallel plates of the capacitor here. Because of that reason it is giving WL/COX amount of the capacitance in the cutoff region. And next, constraint extension. Constraint extension means when we are constructing the MOSFET, we are taking one P type of substrate and we are inserting two N type of materials to make the drain and source terminals. And similarly, to make the gate terminal, we are taking the silicon dioxide layer as well as this semiconductor material again. So here instead of till this point, if it is extended till here and this one also extended till here, and in this case also it is extended till here and it is extended till here means, so because of this extension of silicon dioxide layer as well as the polysilicon layer, the capacitance will existing across the drain and source terminals. So the overlap length, how much amount of overlapping is occur, we are indicating with LOV, and the overlapping capacitance we are indicating with the COV here. So the overlapping capacitor we are indicating with the width and length of the channel as well as COX. And the overlap length, how much it is extended here means some 0.05 to 0.1 amount here. And the half part of the COV capacitance is added to the CGS capacitance, that is gate and substrate, and half part is added to the gate and drain terminals. So these four are the capacitances which are existing across the gate of the MOSFET. So that's why these four are called as the gate capacitances of the MOSFET. And second category of the capacitances which are existing in the MOSFET are junction capacitances. So two types of junction capacitances are existing in the MOSFET, that is between the source and body and between the drain and body here. So here for source diffusion, the source to body reverse bias capacitance can be determined by utilizing this formula, that is C source to body equal to CSPO by under root of 1 plus VSP by VO, where CSPO is nothing but the capacitance value at zero reverse bias condition. That is at zero reverse bias conditions, we are not providing any bias in here. And VSP is nothing but the magnitude of the reverse bias voltage, and V0 is the junction built-in voltage, almost with the range of 0.6 to 0.8 volts. So this is the formula of the source to body capacitance. And similarly, if we calculate the drain to body capacitance, whenever the reverse bias is applied to the MOSFET. So in that case, it is same. It is similar to the source to body capacitance only. The thing is, instead of capacitance CBSO, we are having CDBO here. So where CDBO is nothing but the capacitance value at zero reverse bias condition, and VDB is nothing but the magnitude of the reverse bias voltage, how much we are applying between the drain and body regions, and V0 is the junction built-in voltage, and this is also range from 0.6 to 0.8 volts here. So these two are the two junction capacitances which are existing across the two junctions of the MOSFET. So in this session now, we discussed what is meant by capacitance and what are the different types of capacitors which are existing in the MOSFET circuit, and how we can calculate that capacitances also we have discussed. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.